So what we want to do today is, I'm going to use this pen. We're going to start with the name. This is object. Object, boy. No, I'm using a stylus. I don't have good penmanship. So that's not good enough, huh? Object. Maybe if I lay it flat.
Did something right.
Ha! There we go. So I think I lost some of that recording. I think I stopped recording when you guys started complaining. So let's do step 2 and step 3. What's step 2? Free body diagram. And step 3 is coordinate system. Very good. So, this object rolling down the incline is translating down the incline in a linear fashion. So what type of coordinate frame do we want to use? XY. Cartesian coordinates, where X points in what direction? Down the incline, because that's the way it's moving. So I'm going to draw an X direction down the incline and a Y direction perpendicular to the incline, perpendicular to the motion. And then X cross Y is Z, where Z is out of the board, out of the page. Okay. Then I draw my rolling object, my mass. And what are my forces acting on this object? Gravity, the weight, and it acts from the center of the object. All three of these objects have a center of mass in the center of the object. Okay, there they are. They're all homogeneous objects. Now, as I'll go through later in the lecture, we'll investigate what will happen if the center of mass is not in the center of the object like it is in this particular problem. Right here I have another homogeneous disk, but then it has attached to it a mass close to the edge. So now the center of mass will be off of the center of the object. Okay, so we'll investigate how that changes the problem. But for now, we just have the weight acting through the center. Now, what else do we have? A normal force, and the normal force acts at which point?
Where it's touching the surface.
Right, the contact point, which we have been calling point P. Okay, point P is the contact point, and we'll talk more about point P when we get to constraints. So, this is the normal force, and it acts at point P. And then, what else do I have? Friction, and it moves up the incline or down the incline? Up the incline. Anything else? No, that's it. All right. Now, if I go to step 4, step 4 is sum of forces equals mass times the acceleration of the center of mass, as well as the sum of moments about the center of mass equals IZ center of mass times theta double dot. Now, looking at the X direction, which you'll have to look at your notes because it's not on the page here. That's kind of one of the disadvantages I can see already. Sum of forces in the X direction equals the mass times the acceleration of the mass in the X direction. X double dot center mass equals, what are my forces acting in the X direction? Friction in which direction? Negative, yes, negative force of friction. And a component of the weight, which component? The sine, yes, so plus mg sine of phi. So if I go back here and maybe pick a different color. Then this has a negative y component, positive x component, where this angle in here is the angle phi. So in the y direction, do I have any motion of the center of mass in the y direction? No, so it has zero acceleration in the y direction. What are my forces in the y direction? Positive normal and minus, all right, mg cosine of phi. Then I do my sum of moments about the center of mass equals Iz, center of mass, times theta double dot equals, what are my moments? Right, the only moment is caused by the friction. The normal force, the line of action of the normal force passes through the center of mass. And so, and the mass times gravity obviously acts through the center of mass. So the only thing we have is the force of friction. Is that positive or negative moment? Negative moment. And what is its perpendicular moment arm? R, the radius of the disk or the object. So I have minus force of friction times R. Okay, I'm going to try and put knowns and unknowns on the same slide. Knowns and unknowns. So, going equation or variable by variable, m. X double dot center mass. That's the equation of motion we're trying to find. Force of friction. Gravity. Phi. Normal force. Iz center mass. Yeah, Iz center mass is known. We can actually look that up. So whether it be a sphere, a disc, or the cylinder, you can simply look in Appendix C of your book to determine what that mass moment of inertia is. I'm sorry, can you see that low on the board? Not really? I need to, okay. I will stay above that for now on. Theta double dot. Unknown. And then the radius, R, known. So here we've got, if we look at this, right, we've got 4 unknowns. But we have 3 equations. Okay, so we need a constraints equation. All right. Step 6, constraints. What is my physical constraint?
That the force of friction is going to be equal to normal force times.
Nope. Yeah, no slipping. Rolling without slipping is my physical constraint. Rolling without slipping. Okay? Rolling without slipping. So if an object is rolling without slipping, then the velocity of the contact point, the point P, is 0. It has 0 relative velocity to the ground, or else it would be slipping. Okay? And so the velocity of contact point P is 0. That is the constraint. Okay? That is always the constraint for rolling without slipping. All right? The question now becomes, how do I use that equation to get an equation relating at least 2 of my unknowns, so that I get another equation that has my unknowns in it, so that I'll have 4 equations for unknowns. So how I do that is using one of the equations on your equation sheet, the relative velocity equation. In this case, I want to relate the velocity of point P, which I know, to the velocity of the center of mass. Okay? So the velocity of point P is known as zeros equals the velocity of the center of mass plus omega cross with r of point P with respect to the center of mass. Okay? So I have the translation of the center of mass of the disk plus omega of the disk cross with r of point P with respect to the center of mass. So the translation plus a rotation gives me the velocity of point P. Okay? Now the velocity of the center of mass is simply x dot of the center of mass. And is there any y dot of the center of mass? No, not in our coordinate frame. So it's x center mass dot and 0. Okay? Then I need this cross product. So plus a cross product in our xyz frame of omega. What is the omega vector in our xyz frame? Does it have any omega in x or y? No, right, those are 0. Yeah, I have pure rotation about the z-axis. So what do I put in z? Theta dot, right? We have this theta double dot, our angular acceleration of our disk. So now this is our angular velocity of our disk, theta dot. And again, we assume it's positive. We assume positive, let the minus signs come out in the math. Okay? Then I need the position of point P with respect to the center of mass. So let me backtrack to our picture here. So here we have the center of mass. Here we have point P. Does it have any x position? No. What is its y position of point P relative to center of mass? Right, minus r. Right, r in the negative y direction. So I have 0 in the x and minus r in the y and 0 in the z. So this cross product, what this becomes, is in the or in the x direction I'd have 0 times 0 minus a minus theta dot times r. So I have a positive r theta dot in the x, and then in the y I'd have 0, and of course in the z I'd also have 0. So combining this with my velocity of the center of mass, which only has x velocity, I simply have x dot of the center of mass plus r theta dot equals 0. So if x dot center of mass equals minus r theta dot, getting the r theta dot on the other side, then I simply need to take the time derivative of this function to yield that x double dot of the center of mass is equal to minus r theta double dot. That is my constraint equation. Now I have 4 equations, 4 unknowns. Okay? Now you probably could have intuitively determined this, that positive x velocity yielded negative. So if I have positive x, my object has to rotate clockwise or negative rotation. So in this case, it's pretty intuitive. But in a different case, like this case, where the center of mass is not in the center of the object, it's less intuitive. So going through this relative velocity equation is pretty much required in that case. Okay? In a simple case like this, sure, I expect you to just say, oh yeah, x double dot of the center mass is minus r theta double dot, right? It's simple. But the true constraint for rolling without slipping is the fact that the contact point between the object and the surface has 0 velocity. Yes, sir?
Can you go back to the previous slide?
Okay. So now with 4 equations, 4 unknowns, I want to solve the equation of motion, which will be for x double dot. So I want to use this constraint equation to replace the theta double dot with x double dot and then solve for my remaining unknowns. Okay? So So this is step 7. Solve for the equation of motion, which in this case is x double dot of the center of mass There's one of the equations I need, the sum of forces in x. Now, that was nice, huh? So what I want to do is I want to get the unknowns on the left and keep the knowns on the right, just like before. So I'm going to have mx double dot of the center of mass plus the force of friction equals mg sine theta. Or, I'm sorry, sine phi. Uh-oh, where's my eraser? There we go. So that is my first equation. My second equation will come from my sum of moments equation. We'll just copy that over. Whoops. Where was that eraser? No, don't do that. There we go. All right. So now what I want to do is again get the replace the theta double dot using my constraint equation that theta double dot is minus x double dot of the center of mass divided by r. So now, again, I want to get all the unknowns on the left. So I'll have IZ center of mass times a minus x double dot of the center of mass divided by r plus force of friction times r equals 0. Now I have two equations and two unknowns for x double dot and the force of friction with the previous equation and this equation. But I'd like to use the matrix vector method to solve this two equation, two unknown system. And so in order to make this nice, I'm going to eliminate the fraction here by multiplying by r. So I'm going to have IZ center of mass times, or minus IZ center of mass times x double dot of the center of mass plus the force of friction times r squared equals 0. And that's going to be my equation 2. All right. So we've got this previous equation, equation 1, from my sum of forces in x, and equation 2, then from my sum of forces, or sum of moments, and the constraint equation. Now I'm going to put this into the matrix vector method, where my two unknowns are x double dot to the center of mass and the force of friction equals all my known information. So from my first equation, what multiplies x double dot to the center of mass? M. And how about force of friction? 1. And then what's left? mg sine phi. And then in my second equation that's just above this, I have minus Iz center of mass times x double dot center of mass plus r squared times the force of friction equals 0. So this is in the A times x equals B form. So now what I want to do to solve for both the x double dot center of mass, which is is the culmination of step 7, and the force of friction, which I'll actually use in step 8, is to take the inverse of A to solve for both of those. So let me go ahead and copy this over to the next slide. And so x double dot of the center of mass over the force of friction is equal to 1 over the determinant of A. The determinant of A would be m times r squared minus a minus, so plus 1 times Iz center of mass times the cofactor matrix. The cofactor matrix for a 2 by 2, you flip the main diagonal, so r squared is in the upper left and m goes in the lower right. And then the off diagonals become negative of what they were. So we'll have minus 1 in the upper right and a positive Iz center of mass in the lower left times the b vector mg sine of phi and 0. Solving for x double dot of the center of mass, I have x double dot, the center of mass, is equal to r squared times mg sine phi, and then minus 1 times 0. So I just have mg r squared, the sine of phi, divided by m r squared plus Iz center of mass. That is my equation of motion. Now notice that it's a function of Iz center of mass here. Okay, this Iz center of mass has units of mass times distance squared. So like kilogram meter squared or slug foot squared. Okay. Now, because this will have a mass in it, it actually doesn't matter if all the masses are equal, because the mass will cancel out of the equation. Okay? What will be important is the function or the constants outside of this mass moments of inertia. So, again, if we look up in a table what those mass moments of inertia are, basically, the lower or the smaller the mass moments of inertia is, the faster it should rotate. The larger the mass moments of inertia is, the slower it should rotate, because the more energy goes into rotating the object than translating it. Okay? So, if we look at these mass moments of inertia is proportional to, or is a measure of the distribution of the mass from the center of mass. Well, all three of these have the center of mass in the center of the object. So which one has the mass farthest distributed from the center of the object?
Cylinder.
The cylinder, right? So its mass doesn't have any mass in the middle, right? All of its mass is distributed far away from the center of mass, or center of the object, which is why it finished last. Okay? Now these two, the sphere and the disk, are really close. Okay? But as per the demonstration, we know the sphere has a smaller mass moment of inertia than the disk, but only slightly. We can visualize that by thinking that the sphere, we can make the disk a sphere if we kind of cut off some material off these outer edges and attached it to the sides, right? That would make it very close to a sphere. So we're taking mass away from the outside and putting it closer to the middle, okay? Decreasing its mass moment of inertia. So this has a slightly higher mass moment of inertia than the sphere, but only slightly. Okay? So if we go to step 8, solve the equation of motion, solve the problem. Is my penmanship getting better? A little bit. If we go into an appendix, and for you guys it's an appendix C, there's a table full of mass moments of inertia. For a sphere, it's 1/2, or I'm sorry, that's not right. No, for a sphere, it is 2/5 mr squared. For a disk, it's 1/2 mr squared. And for a cylinder, it's 1/2 m times the inner radius of the disk squared plus the outer radius of this disk squared, and the outer radius is simply r for all three cases, so outer radius squared. Okay, so in the sphere's case, we've got 0.4 mr squared. In this case, we've got 0.5 mr squared, so just slightly greater than. And then in this case, it's quite a bit greater than the disk because it has the 1/2 mr squared term. But in addition to that, it has an 1/2 mri squared. So it's quite a bit bigger than that of the disk. Okay? So if we look at our little race again, right, the sphere will only slightly beat out the disk, but the cylinder will trail by a pretty good margin. Okay? And also you notice that in all three of these, there is the variable m, the mass. So when if we would replace these functions into the equation of motion that we determined in step 7, we would have a mass in this term, mass in this term. We could pull out the mass, and that cancels with the mass in the top term. Also, in the case of the disk and the sphere, right, all three terms would have an mr squared. So an mr squared would cancel that everything. And the equation of motion would simply be a function of gravity and the sine of phi, the sine of the incline. Okay? Are there any questions on that? Yes?
So if we had a thin-walled cylinder, it would also be mr squared?
A thin-walled cylinder?
Yeah, so...
like this?
Yeah.
But it's just thin?
Yeah, it's really thin, so you can say it's just r.
No.
So it would be mr squared.
No, your inner radius and outer radius would just be related through the thickness t. That's all.
Okay.
You're talking like theoretically
Yeah.
thin cylinder?
Yeah.
It would be imaginary.
Yeah, right, if you just have a thickness, then you just relate the inner radius to the outer radius through the thickness. Okay? Yeah, the thinner it gets, the higher its mass moments of inertia. It'll get slower and slower and slower.
All you're trying to do is just roll all into cylinders down and things.
Okay? And again, the higher, the larger the mass moment of inertia, the more energy it takes to spin it up, which means the slower it will translate. All right? So that solves the problem of which one comes in first, second, and third. So because these are in order of I decreasing. Oops, I'm going to go off the page. Sorry. Our I is decreasing. That means the sphere wins, the disk places, and the cylinder shows. Yep, let's go to the races. Anybody care to take a bet now? All right. Now the other part of this problem is we have assumed that the object will roll without slipping. Okay? What if that's not true? How do we determine whether that's true? Okay? So how we determine whether it slips or not has to deal with friction, the other unknown that was in our two-equation, two-unknown system. Okay, so let's solve for friction. So again, I'm gonna copy this part. No, never mind. I'm gonna copy this part. And if I solve for the force of friction, the force of friction will equal IZ, center of mass, divided by mr squared plus IZ, center of mass, so that's a ratio, times mg sine of phi. Okay, since I have IZ, center of mass, times mg sine phi, plus m times 0, all divided by mr squared plus IZ, center of mass. Okay, so that's the force of friction. What must this force of friction be less than? Static friction. Why is it static friction? Well, because the velocity of that contact point is 0. Okay, that relative velocity between the surface and the disk, or the rolling object, has 0 velocity. So it is static friction. So it must be less than or equal to mu sub s times n. Well, n was our fourth unknown in our system. From our sum of forces in y, n would be equal to mg cosine phi. Okay, so this is mg cosine of phi, which means the mg's cancel. I can bring the cosine on the other side to say that mu sub s must be greater than or equal to IZ, center of mass, divided by mr squared plus IZ, center of mass, times the tangent of phi. If that is true, it rolls without slipping, which makes perfect sense because if phi is 0, mu sub s just has to be positive, which it is. So obviously if it's just here, it's not going to slip. Okay? As soon as I have incline though, mu sub s has some minimum value. If it's less than that value, it will slip, and then we have a 2 degree of freedom problem, right? We have translation in x as well as rotation about theta, and the difference then would be we have an addition. Our constraint in that case would be the force of friction is equal to mu sub k times n, right? Kinetic friction. So what did that look like? Probably something like this. Now, really, what you wouldn't be able to see it because I don't have any markings on the side. But what you're listening for is this. Okay, so it's sliding as it's rotating, and that's because this inequality is no longer satisfied. All right. Now, this concept actually is involved in anti-lock brakes. Okay, so anti-lock brakes, the way they work is they want to keep your wheel rotating without slipping. Okay, because if they're rotating without slipping, then force of friction is less than or equal to mu sub s times n. Now, in the case where you're trying to maximize your deceleration, the force of friction is very close to that maximum value because it wants to slip. Okay, but if you're pumping, right, if the anti-lock brakes are pumping them so that they don't slip, then that force of friction, which is very close to mu sub s times n, will be greater than mu sub k times n, causing you to stop quicker. Okay, so that's again the concept behind anti-lock brakes: rolling without slipping versus rolling with slipping. Right? All right. So the last step of this is obviously step 9. Does it make sense? Of course it does, right? So first of all, magnitude. If we think about magnitude, really what we're talking about here in this particular case is did they finish in the way they were supposed to finish, right? The magnitude of their acceleration, the magnitude of the acceleration of the sphere was greater than the magnitude of the acceleration of the disk, was greater than the magnitude of the acceleration of the cylinder. They finished in the order they were supposed to. The magnitude fits. We could also look at a specific acceleration if we wanted to. For example, if we looked at the acceleration of the disk had an IZ center mass of 1/2 mr squared. Well, the mr squared would cancel in all terms. We'd have 1 plus 1/2 in the denominator, so 3/2 in the denominator, and 1 g sine phi in the numerator. So 1 divided by 3/2 is 2/3, so we'd have 2/3 g, so something less than gravity, times the sine of phi, which is going to be small. So it is going to be a small acceleration, much less than gravity, but still positive. Okay, so the magnitude does make sense. Can't accelerate faster than gravity, and that is proven through that simple analysis. So magnitude makes sense, and then the signs. We have positive acceleration of x, negative acceleration of theta, and our mu sub s had to be positive. Okay? All of those make sense. And then finally, the units. So if we go back, the units on our coefficient of static friction here, this term would be unitless, right? Kilogram meter squared divided by kilogram meter squared plus kilogram meter squared. So that's unitless. Times the tangent of phi, that's unitless. So mu sub s is unitless. That's good. Force of friction, we have unitless times mg, newtons, times unitless. So it has the same units as mg, so that's unitless. That's good. The units on acceleration. Our acceleration, right? We have, again, mr squared plus something that has kilogram meter squared in it, or slug feet squared in it. So all those units cancel, leaving units of gravity times the sine of phi. Sine of phi is unitless, so it has the same units as gravity, whether that be meters per second squared or feet per second squared. All right? So all those units check. So I know that I have the right answer. Okay? Now, I'm going to go ahead and stop this.